Okay, we're going to continue with sort of the next topic. So here, when we start talking about pathway enrichment analysis, we start going at a higher level of organization of the data and start thinking also about coming much closer to interpretation. So a good way to think about pathway enrichment, essentially, this is one of the key biological questions of interest, is whether a set of functionally linked compounds is differentially expressed across two conditions. So for example, we saw that in the SWAN data, after all the results that I have shown you, for various reasons, we cannot identify too many differentially statistically significant metabolites. However, there might be still some very interesting biology going on if instead of looking at individual compounds, we start sort of mapping them to canonical pathways and then asking the question at this higher level of organization. So pathway enrichment analysis has by now fairly long history. This is an excellent reference, although it's almost 5 years old. It summarized a lot of the developments by that time, and since then there haven't been that many sort of new developments, at least for the first two types of pathway enrichment methods that are also implementing MetaboAnalyst or in other platforms. The third one is a topic of active research, and then things get much, much more complicated. And at that point, if you really want to use some of these more powerful methods, you need to switch to R and find the appropriate package. So Ala is gonna, 5 minutes from now, have a full presentation and is gonna sort of talk much more. So this is pathway enrichment analysis. Of course, started, is very popular for gene expression data, and even earlier, people were using sort of to look for enrichment of gene ontology terms. And this schematic is taken from this review paper that I mentioned on the previous slide. So essentially, what you need is, your data, and then, of course, some information to extract the pathways, because you need to know which metabolites belong to which pathways in order to create those sets. And then you do some mechanics in order either to carry this type of analysis or this type of analysis. I'm not going to mention anything on that because this is still an evolving field. So overrepresentation analysis, as I said, is a very old technique, and it was motivated by questions regarding enrichment of gene ontology terms. So one thing that, how are the mechanics? Essentially, you're going to create this 2x2 table, and you need two pieces of input. One of them is to have declared, maybe after FTR correction, a list of differentially expressed compounds. Here it says genes, but any omics, for any omics data set, it's the same idea. And then you arrange your data, after you have made this call, on this 2x2 table. So you have the compounds that are differentially expressed and belong to the pathway of interest. Let's say the amino sugar pathway. And then there are all the compounds that are non-differentially expressed and belong to the pathway. And then essentially you look at the complement sets, and essentially you have your 2x2 table and the totals and so forth. So for this, essentially what you're asking is whether this entry in the 2x2 table is significantly higher proportionally, given sort of how big your pathway is and how many differentials you have, than what would imply by mere chance, and essentially that sort of Fisher's exact test. Or if you're looking at a lot of compounds, you're going to do a chi-square test. These are minor differences at the technical level. So therefore, for every pathway, this test is going to spit a result, essentially a p-value, and tells you whether the pathway is significantly enriched or it's not enriched. And of course, then, given the fact that you get the p-values from, let's say, testing all the canonical biochemical pathways, you need again to adjust for multiple comparisons, because unless, for whatever reason, you're only looking at one pathway. It's exactly the same issues that we discussed yesterday. So there are, so the mechanics of, for the functional scoring methods, which is the new generation, it came up with the famous gene set arrangement analysis paper that came out of the Broad, and many of you may have used that type of tool, is it works somewhat differently. If you look at how you construct the input for carrying out this test, here before you even start populating the table, you need to make this decision of what you call differential. On the other hand, for functional scoring methods, you don't have to make such decisions. The only thing that you need to decide is what type of statistic you're going to use, either a t-statistic, so the value of the t-statistic, or even a fold change. All these things work. And then you compute a pathway enrichment score that essentially aggregates in appropriate manner the gene level statistics or the compound level statistics. Maybe the median, it may be the mean of all the t-statistics or the mean of all the fold changes in the pathway or the ranks or something more fancy. There is a whole slew of alternatives. But essentially, if you think of what these functional scoring methods are trying to do is they are not using the information in the pathway who is differentially expressed or not, essentially a 0-1 information, yes, differentially expressed, not differentially expressed, and then let's see whether we have adequate differentials within the pathway, which was the previous version. But they say how much evidence we have that there is some degree of differentiation, even if it's not at the, you don't reach level of significance for all the members. And therefore, let's sort of aggregate them, because this is much more in concordance with the key idea that together a set of functional link compounds is differentially expressed. So what may happen, for example, under this set of methods is that you don't, potentially, you may still call a pathway as enriched, even if none of the compounds in the pathway are differential. And the reason is that all of them may be different, but not significantly different. But as a set, they contribute a lot to raise the level of significance for the pathway. So this is a much more sensitive statistic, and in many cases works much better than over-representational analysis. And then, yes, sure.
Set of things in that pathway, but a couple, 2 or 3 factors that are very significant, because that skew the whole pathway too, to get the same, even though it's very different. So having anything just a little bit not quite significant.
Yes, yes, yes. So for the first scenario, if nothing was, let's say, significant, this method is not going to pick anything because all of these here are going to be 0. So this method is not going to call it significant. On the other hand, if you have this coordinated activity, although none of them is very strong, but all of them are moderately strong, and they don't pass individually your threshold, let's say, of 5%, then you're going to call the pathway significant. Of course, that doesn't prevent the extreme event that you described. Let's say that our pathway has 10 members, 3 of them are very, very significant, and therefore the t-statistics are off the roof, and everybody is not significant. Then, in all likelihood, again, you're going to call the pathway significant. So that means that in many cases, you may want to, once you get the results, you may want to go back in order to see exactly what goes on, and whether you're in the latter setting, to see that maybe you call something significant because there were 2 extreme members or 5 extreme members out of a larger set. So you may want to do follow-up work, because the method is agnostic to the 2 scenarios. Very good point. So some key issues for metabolomics pathway enrichment analysis right now that we have a very rough idea of the mechanics is The coverage of the metabolome may not be complete. For example, when you use gene set enrichment analysis, essentially you're dealing with much larger pathways. You have much better assays. Here, one of the issues is that, for example, if you do a targeted assay, some of the pathways, you may only have seen data for half of it. So you have these issues of coverage, and therefore, when you test, essentially you have data for 3 members out of a larger pathway. And similarly, if you have a lot of unnamed compounds. So this is something that you always need to think a little bit about. The other thing that happens, obviously, is that, some compounds may belong to multiple pathways. So when, for example, you do the multiple comparisons correction, you need sort of to address it appropriately. So that's the second point, that these metabolite correlations also induce positive dependence between pathways, and therefore, instead of the classical FDR procedure that essentially is built in all the software, there are better techniques. Unfortunately, they're not built in all software. So that's something that you need to be a little bit cognizant about. So in terms of, so essentially these are the few things that I want to say about pathway enrichment, and essentially just to give you a glimpse of the mechanics. But going back to the entire presentation, software tools, the moment you can do a little bit of programming, this is a very, 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 very rich set of tools. Essentially, you can do all the analysis that we described and even much more fancy analysis. Metabo analysis has come a long ways, as you're going to see in the demos. There are some other available tools, commercial packages. Some of the best techniques actually have just started appearing in some of these commercial packages. So, for example, the nice plot that you asked, that Farsad made, he made it in the SPSS, but it's easy to program in R. So it's an active field, and it depends on how deep you want yourself to go in the analysis. If you really want to be able to have complete control of your analytic pipeline, I'm afraid you have to learn R, because that's where the community contributes a lot. And on that note, I'll switch to Allah.